Hello, and welcome to my SciTech 2021 presentation. Today I'll be discussing finite dimensional density representation for Aerocapture uncertainty quantification. I want to begin by thanking my co-authors, Dr. Ali Reza-Doustan, and my advisor, Dr. Hans-Peter Schaub. Begin by briefly covering the concepts of uncertainty quantification and Aerocapture. Then I'll go through our use of a Karhunen-Loève expansion to represent density variability for Aerocapture. And we'll finally show our implementation of that method using polynomial chaos expansion and then comparing that to the performance of Monte Carlo analysis. We'll show some preliminary results, as well as touching on one issue that arises when you use this method for the Aerocapture problem. Briefly, we'll touch on future work steps, and there will be a live Q&A. So when we talk about uncertainty quantification, we mean we have some model and there are uncertain inputs to that model. We want to estimate some statistics of interest for the outputs of that model. Monte Carlo is by far the most popular method to do this, and it's popular because its convergence rate is independent of the dimensionality of the problem. Where here, by dimensionality, I mean the number of inputs which are dispersed or random. It is not, however, the only method available. There are many. I've listed a few here, including polynomial chaos expansion, which is what we'll focus on today. And in general, the goal of these other methods is to converge more quickly, meaning they can they can estimate the statistics of interest with the same accuracy using fewer samples, which reduces the number of times you have to run your simulation or your total computational load. One obstacle to using these other methods, though, is that in general, they require a finite representation of the uncertainty of the problem, finite dimensionality D, and furthermore, they begin performing poorly when that dimensionality becomes high. So to quickly define the Aerocapture problem, a spacecraft is approaching a planet or moon with an atmosphere, usually on a hyperbolic orbit. It uses the atmospheric lift and drag forces to reduce its energy and reach a desired orbital state that's captured, and then it will perform a single maneuver to raise its periapsis back out of the atmosphere, followed by any corrections that are necessary. The main uncertainties for this problem can be broken into these three categories: vehicle related, navigation state related, and uncertainties related to the atmosphere. Most importantly, the density variability. And there's inherent variability in the density of the atmosphere, as well as our own limited understanding of the complex physics at play. So we're dealing with both aleatory and epistemic uncertainty here. And it's also important to note that unlike vehicle and navigation uncertainties, atmospheric uncertainty is, well, density is a continuous function of altitude. So it's modeled by a continuous random field, and since it is continuous, that actually has infinite dimensionality when you represent it as a continuous random field. So that is an issue that we need to overcome. So let's talk about what common approaches there are for representing density and its variability for something like Aerocapture simulation. There's really two main approaches here. One is to use a model such as an exponential atmosphere model, and that's very simple. It's essentially a curve fit to the data, but it tends to be pretty accurate. And you can disperse a model like this by randomly selecting the surface density and atmospheric scale height from some distributions. So you can get random density values, but they will still all be on the shape of the atmospheric density profile will always be the same. And so it doesn't have very high fidelity. It's not particularly realistic. And then on the other end of the spectrum, we have black box models like IMSIS or the global reference atmospheric models. And these are higher fidelity and more realistic, but they're usually treated as a black box, just outputting a new random profile every run. And so that's going to be very high dimension. Really, its dimension would be equal to however many steps you've discretized your altitude profile into. And so our goal here is to find something that's in between these two extremes that has the physical realism of a model like Graham, but has a lower number of stochastic dimensions so that we can use some of these other techniques. So we've applied something called a Karhunen-Loève expansion to do this. It's a generalized Fourier series expansion. And then we'll truncate this infinite series expansion to some number D terms, where we can select that number of terms based on the percent of total variability that we want to capture. And by the way, here we're using as our truth model just a large number of runs from Graham. But you could easily use a different model or even just raw data to do the same process. This table in the lower right is showing results for Mars-gram, where you can see that if you want to capture 95% of the variability, that just takes 14 terms or 14 dimensions just for the density variability. But if you go up to 99% of the total variability, you need 64 terms. So there is a steep increase here as you reach very high levels of, very strict error thresholds. But if you do something like this for your density model, you can now model Aerocapture using, I've used D plus C dimensions, where C is the number of other inputs that you're dispersing. And so this makes possible some of those other methods it makes it possible to apply some of those other methods that we mentioned to the Aerocapture problem instead of just relying on Monte Carlo, while still using a density model that is a little more realistic than an exponential fit. So to demonstrate that, we chose to use polynomial chaos expansion, which is, again, a generalized Fourier series expansion, this time using orthogonal polynomials. And we'll again truncate the series, this time such that we have a basis of total order P in terms of those polynomials. And then we have this series, and we need to estimate the values of these coefficients C. And there are a number of ways to do that. We've chosen to use compressed sensing, which essentially can bootstrap the problem by using a small number of randomly generated samples to estimate the coefficients. And in fact, it can get good estimates even for the underdetermined problem, meaning there are fewer samples than there are coefficients. It does this by enforcing sparsity in the coefficient vector. And of course, there's more detail in the paper. An important thing to note, though, is that the convergence of this method depends on the regularity of the output with respect to the input. And to go back one step, another important thing about compressed sensing to note is that it is non-intrusive, meaning we don't need to modify our solver to use this technique. We can just generate a small number of random samples, and that allows us to estimate the value of these coefficients. But as I was saying, we have to assume this smooth relationship between the input and the output. And as I'm showing here, that's not actually always a good assumption for the Aerocapture problem. Here I'm showing the results in terms of the flight path angle and the orbital energy at the final state for a large number of Monte Carlo simulations. And for cases that successfully Aerocapture or cases that end on a hyperbolic orbit, the states vary smoothly, but the final states of any cases that impact the surface are way over here. They're discontinuous in terms of the final velocity and final radius, which leads to this discontinuous jump in most of the useful parameters that would describe the final orbital state. This is important to note because if you have input dispersions in your problem that are large enough that you have any significant number of cases that impact the surface, even if those cases are outliers, that can lead to worse convergence or even failure to converge of your PCE method. And so we demonstrate that and other things here. This is a sample of the results that are shown in the paper, where we're showing that, yes, indeed, PCE converged for this problem, and it did outperform Monte Carlo for small sample sizes, where you can see this one behaves nicely, where the PCE method really hits a floor in terms of accuracy here because we've truncated the order of the expansion, whereas the Monte Carlo accuracy will continue to decrease, but at small sample sizes, you can get good accuracy, much better than Monte Carlo, with a smaller sample size. So the benefit here is that you could use a smaller number of samples to get a reasonably good estimate, and that way go through something like a large parameter sweep much more quickly. We also showed that the data does converge better if you filter out the impact cases, but obviously that has its own drawbacks since you won't capture their behavior in your PCE application. So finally, there's a lot of future work to do here, mainly on the polynomial chaos expansion results. We have some cross-validation to do, and also optimizing the value of a sigma, which is really just a tuning parameter in the PCE implementation. And those are steps that we'd like to do before we can feel more confident making conclusive comparisons between the performance of PCE and Monte Carlo for this problem. And there's some other additional work that we'd like to do. I'd be very happy to discuss them in the live Q&A. And thank you for watching.